Train A runs back and forth in east-west section. This is the velocity. It's differentiable. You have the velocity of train A, so they put a little A in there, but whatever. Okay, average acceleration. So quickly, what do you do? What do they ask for average acceleration? So their slope. They just want the slope, right? Slope between 2 points, right? Average, again, when you see the word average, the average is going to have two uses in calculus. It's going to have average value, where you do an integral. That's the average of an integral. Now, if you would have had an acceleration function, right? If you'd have had an acceleration equation, and they asked for the average acceleration, then that would be that average value formula, right? The integral of the acceleration. And I think I even showed you where those are connected. If they ask for the average acceleration from 2 to 8, right? That's one way to get the average acceleration from 2 to 8, the average value function. But do we have an acceleration function? No, we have a velocity function. But here's where they're connected. Where they're connected is, if you were going to work this out, what would fundamental theorem part 2 tell you about the integral of acceleration? It's velocity, right? So this would be v of 8 minus v of 2 all over 8 minus 2. But what is that? Well, that's it. That's an average acceleration, but it's average rate of change. It's what Jesse just said. You do the slope. It's basic. So when they say average acceleration, we actually take the velocity values and do a slope between those 2 points, right? So that's the connection there. You probably didn't think of this at all. You probably just thought of that, which is fine, because the average acceleration can be meters per minute So we're going to take meters per minute. So we're going to take negative 120, and we're going to minus 100 over 8 minus 2, and so what is that, negative 220 over 6, right? On the AP test, you could actually leave that at that point. You would not have to reduce that. Negative 110 over 3 probably would reduce. You could go to a decimal, but this is where I was talking to some of you guys the other day, or on an earlier quiz. I mean, even some people is this a no calculator or calculator? No calculator. I mean, even on the no calculator, remember there were some of you, I don't know, it might have been the other class, that were doing long division here, right? Don't do that. Don't, it's kind of a waste of time. Just leave it like this. I'm kind of curious here. I think I do have the answer thing here. So, yeah, so they, now, they didn't say anything about showing your work or anything here. Sometimes they do, oftentimes they do. Sometimes they give you a point for showing that work. But here, average acceleration, they just gave 1 point, basically, for the answer. Units, I would always put units on. But in this case, if you didn't have the units, you were going to be okay. If you had that right answer, you were going to be fine. Okay? But they did reduce it like that. But again, if you had 220 over 6, you would be okay. All right, what about B? Does the data in the table support the conclusion that the velocity is negative 100 meters per minute sometime between 5 and 8?
Yes.
What do you state to help you with that?
Intermediate value.
IVT, the intermediate value theorem, right? Now, somehow you want to get in the idea of the hypothesis of the intermediate value theorem. Remember what it was. If a function is continuous on a closed interval, so from 5 to 8, on the open interval too, but I mean, if it's on the closed interval, then it has to hit all the y values in between the endpoints. Well, between 2 and 5, the endpoints, no, what was it? 5 and 8. So between 5 and 8, the velocity goes from 40 to negative 120. Somewhere in there, it's got to be negative 100. Because the function's continuous, why do we know the function's continuous? Because they said it was differentiable. Remember, any function that's differentiable is always going to be continuous. So that's what they're saying right here. You had to have that in there, and you couldn't just say the intermediate value theorem, though, right? You can't just say because of the intermediate value theorem. You got to talk about what the intermediate value theorem says, okay? At least the hypothesis. The conclusion you don't have to state. It's not like you have to state the whole theorem, but you guys memorized it for that quiz, so maybe you could. But you have to state the hypothesis, right? That shows, okay, we do have the conditions for the intermediate value theorem, and then you're fine, because you obviously know the conclusion, what it means, or else you wouldn't be using it here. But you have to show that you know the hypothesis is met. That's the key. So you say, since this function is differentiable, we know it's continuous, so therefore the intermediate value theorem says, yes, it will hit negative 100 somewhere. Does that make sense? So you wouldn't have to really state the whole theorem, but you're going to have to show that if you're going to use this theorem, the hypothesis is met. Okay, we did part C the other day. Okay. All right, so D says a second train travels north from the station at time t. The velocity of the train is given to be this. At time 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between A and B is changing. So which way was train A going? East. So here's the station. So this train is going east, okay? And then this train is going north at this velocity. At time 2, it is 400 meters north of the station. Okay? All right. Find the rate at which the distance between trains A and B is changing. Doesn't that sound like one of those those related rate kind of problems, right? Okay? So what we need, so this was train A, so I'm going to call that A. This is train B, okay? And then this is C. Now all those distances are changing, so we have the old A squared plus B squared equals C squared scenario, right? Okay, so what did we know about this? We know this is 2A, A prime plus 2B, B prime equals 2C, C prime. And what are we trying to find? C prime, okay? Now we can divide the 2's out of there. It would make life a little easier, okay? What do we know about A? Do we know the distance, hey Colin? Do we know the distance of A? That's up above, right? I can't scroll up there right now. What's it say? Oh, that was in part C. Okay? So it's the same time. So at time 2, it was 300 meters east. So at time 2, we know A is 300. Okay, what's A prime? That would be in the table, right? A prime would be how fast it's moving at time 2. And what's that? Positive 100 plus B. They just told us that was 400. And then B prime. You got to plug it into the formula here, right? Plug a 2 in there. What's that? Negative 20 plus 120 plus 25. So 125 equals, and then what's C? Where'd you get 500? 300, 400. This has to be 500, right? 3, 4, 5 triangle. Okay? So 500 C prime. There you go. You got everything you need. Okay? So they sneak that in there. And that's good because, again, people wonder, I don't wonder, but I mean, we do a lot of packets. I understand that. And you do get a lot of problems that are repetitive. But think about that. That's the point. I mean, and people are going to be at various places here. But when you think about the first packet we did, what was when we got ready for the midterm, when you went through that very first packet and all the problems that were in it, how many of those problems looked familiar and felt easy? What percentage, you think? 50? 30? Yeah, I was going to say 50 might be high for some people, but 30, I mean, you know what I mean? I mean, a lot of them, now you go through a packet, I'm hoping it's much higher, right? And that's the point, right? And now when you get to the AP test, you get to the end of the year. And again, what I say is, by the time we finish all of this review of doing all these various types of problems is going to cement, hopefully, some people's cement will be more solid than other people's. people cement, but cement these ideas, of calculus and use them and everything. So when next year you go to count 1 or you go to count 2 or whatever the case may be, that you're going to remember a lot easier. That's the goal. That's the hope. So, but every once in a while, all of a sudden you see that one. We haven't done a related rate one for quite a while. So just when you think, okay, geez, I've seen all these, you keep seeing different ones. So it's hard to do too many of these problems. But anyway, 160 sounds like. So in that one, they gave 3 points, 2 for the implicit differentiation. So in other words, somewhere along setting up this equation and do it so if you made one mistake, you might lose a 1. If you made a second mistake somewhere in the implicit differentiation, you lost another one. If you couldn't get the equation set up and do the implicit at all, then you were going to lose 2, probably all 3, because you weren't going to get the answer either. Okay, let's go to, what do we do, number 6 now? Okay, so number 6, there's just your curve. Let me go back to the other sheet. So if we go to number 6, and they said through the point 0, 1. So, this is just kind of a all or nothing, 1 point, just kind of follow the curve. That's pretty easy. They have enough points in there that it's going to go up pretty steeply probably, but something like that, right? Something like that. And then the second part was write the equation of the tangent line, use the equation to approximate f of 0.2. So you're doing the tangent line at 0, 1. So we need y equals, we need slope. Okay, so how do you get the slope? Geez, God, that was easy. Put it into here, right? So you're going to put a 1 there, you're going to put a 0 there. Cosine of 0 is 1. 3 minus 1 is 2. Is that what you got? 2. So y equals 2x plus 1 is a tangent line. Use it to find f of 0.2. So what do you do with that? Plug in a 0.2. 2 times 0.2 is 0.4 plus 1 is 1.4. 1.4. Okay, with the idea, now understand, that's called a couple of different things. We did a problem the other day where that's called a linear approximation, using a linear approximation. So there's some solution curve, we don't know what it is, there's some solution curve, and we drew it, okay, let's draw it in because it's the same one we just did here. This is our solution curve, right? It's drawn in here like so. Now there's going to be a tangent line right there, right? That's what we just drew, and we found that tangent line to be 2x plus 1. Now, f of 0.2 is going to be on this curve right there. What did we just find with 1.4? We found that point right there, right? So another thing I've seen them do is they would ask, is this approximation an over or under approximation of f of 0.2? Right? Well, in this case, because we can see the picture, it's what? It's an over approximation, right? So this point is actually above the curve. But as long as we stay, and that's why they did 0.2, as long as we stay right in this area, locally linear was a term we used, then that is going to be a pretty close approximation. We get out here, and then the line point will be here, and the curve point's here. It's a terrible approximation. But as long as we stay in here close, right, find the tangent line, plug a number into it, we get a y value that's pretty close to what the curve value would be. Okay, and that's called linear approximation, or a couple different names. And then the over and under, why is it? Because of the concavity. The reasoning would be because it's concave down. When the graph is actually in some books, that's a definition of concavity is the position of the tangent line. Graph is concave down when its tangent line is above the curve. A tangent line is or a curve is concave up when the tangent line is below the curve. Okay, so it's because of the concavity, that'd be an over approximation. Okay, so just a lot of little different things to throw in. Okay, let's go ahead and talk about the new thing for today. So we were going through part C. Oh, did we skip part C? Yeah, because we don't know how to do that yet. So Part C we can't do. So the only parts that are left are part C on 6, and was it A and B on number 2? I think A and B on number 2 we have to learn that. That will come next week. A and B on number 2 will come next week. The lemon, there's anything going on next Tuesday, is there? Golf tournament? Next Tuesday is going to be the lemon slicing.
So we're doing it.
I thought it was going to be Monday too, but now it changed. It's going to be Tuesday. I know. And you got all weekend you're going to be looking forward to. We got the infamous lemon slicing activity. So, yeah, as a matter of fact, let's see. I'm just looking at what's the purpose. Well, find the volume of these lemons. Where is that? Is it in here? Yeah, here we go. That's not a very good picture. They look pretty thrilled. Pretty excited. Yeah, that group was having fun.
This last year.
No. Well, they all say 16 because I think that's when I loaded them up. That was last spring. But those are like Brenna Peterson. That's Brenna Peterson. That's got to be at least 3. Huh?
That's Logan Hansen, and he was a senior and we were freshmen.
When you were a freshman? Yeah, I would say it was 3 years ago. I think it was. That's right. It was, yeah. Schreiner. Yeah, he was 3 years ago. All right. Gosh, it's funny how fast I forget names. Shelby. God, I can't believe it.
Is that Billy?
Yeah. God, I can't believe that. Get these names so fast. I'm getting old. Now?
Yeah, he's here now.
Seriously?
He's always had that up in the bottom. Yeah, it's so long.
It's really long. I mean, it was over.
Does he not cut it? Actually, I think I like just cut it like 2 weeks ago, but it was so long.
All right. Let's see. So let's start here. All right. So this is another one of my stolen PowerPoints. Not stolen. I mean, they gave it freely to borrow. I guess I'm not giving it back because I'm going to borrow it. But whatever. All right. So in your notes. So what we're gonna talk about today is the length of a curve. The length of a curve. Okay. So imagine we wanted to find how long that curve is. Okay. If you think about it, I mean, if I gave you that on a piece of paper and said, measure that, how long is that? What would you do?
Use a string.
Okay, probably get a piece of string and try to lay it along the curve, right? And then what?
You put up the two.
And then take that piece of string, straighten it. That's the key to this. Straighten it so we can measure. In other words, all we can really measure are straight distances, right? Straight lines, not on a curve. So again, in keeping with the theme of calculus, if you haven't figured it out, and I've said it over and over, so you should figure it out, oftentimes what calculus is used for, calculus is often called the mathematics of change, right? A lot of what we do is things you've done in earlier math classes where things stayed constant, and now we've worked in where they're variable. When people talk about calculus-based physics, they do a lot of the physics concepts, but with varying different amounts. In other words, instead of doing velocities, like average velocities, stuff like that, where the acceleration is constant, use calculus-based physics to deal with a varying acceleration. For example, all the physics formulas in high school physics that deal with motion all assume constant acceleration, right? So it's a very similar thing we do with derivative. Okay, slope is slope between 2 points, but slope is just for straight lines. We've learned about slope of a curve. If the graph is actually changing its slope all the time, we found out how to do the slope at 1 point. Now what we did is we took slope between 2 points and got a better approximation, right? Think how we did area. Don't know how to do area under a weird shape? Well, let's do area something we do know how to do, rectangles. Let's do area rectangles and then get better and better approximations, right? I mean, that's what the theme over and over is of calculus. We use the idea of a limit to help us do that. Well, guess what? That's what we're going to do here. We know how to measure straight things, right? But how do we measure a curve? Well, we can't measure a curve. So let's take the idea of measuring something that's straight and let's apply that to measuring on the curve. So if we wanted to approximate the length of this curve, we could take one little segment of that curve. Now they call it ds. Let's call it s for the length. This is going to be the length of that one little bit. But you don't have to write any. I'll show you what I want you to write down here in a minute. But let's measure that short little red length right there. Now notice it's straight. The actual blue curve is what compared to the red line? It's a little more, right? A little longer, okay? Now, if we want to measure that length, let's imagine that to be the hypotenuse of a rectangle. So let's call that, that seems familiar, dx, let's call that dx, like as in delta x, is probably what we normally would put here. When I have you write it down, I'm going to have you write delta x. So it's like the change in x, change in y. Make ourselves a little triangle. And so therefore, by the Pythagorean theorem, that little length is going to be that right there. Okay? Now, let me see where they go from. Okay, I don't want to do that anymore. So, now that's all I want on. Okay, so let's move to a different thing I've got here. All right, and so let's say we wanted to find this blue length right here. Well, one way to do is measure that red length. Well, obviously that's way too short. So, let's go to two lengths. Let's add that one up, let's add that one up, and that seems like it's still not quite enough. So let's do 3. You can see where we're going with this, right? Okay, so let's add up these 3 different lengths. Now, every one of these, we could do what was just on that other picture, right? We could say, okay, let's divide this into, subdivisions. That sounds familiar. Let's divide this up into 3 subdivisions, and then let's do and we'll do our do a little triangle, do a little triangle, do a little triangle, right? And we can find those 3. So by Pythagorean theorem, so we think of each of these 3 pieces here as being a hypotenuse on the Pythagorean theorem. Now you also might say it would just be distance formula, right? But isn't that what distance formula is, right? Distance formula is the Pythagorean theorem. Square root of, subtract the x's, you get this, subtract the y's, you get this, square, and then the square root. So it is Pythagorean theorem. So it's distance formula, distance formula, distance formula. And we get those, we add them up, and there we go. Okay, well, what would make a better approximation? More subdivisions, right? Infinite number of subdivisions. That's definitely where we're going with this. Okay, so you got 4 of them. It's getting better. You got 5 of them. You got 6 of them. You got 7 of them. You got 8 of them, right? You got 9 of them, all the way up to 20. If we do enough of those, right? If we do an infinite number of those, then stop. Okay. We could get better and better approximations to the length of the curve, right? Now, so what we're going to do to create this then is we're going to say, okay, what is the length? How can we write the length of one little piece, right? So we're going to write a formula for one little piece. It's going to be the distance one, okay? Then we're going to want to add up an infinite number of those. What thing do we have that will add something up? The sigma, but when you do an infinite number of things, a sigma turns into the integral, right? We have an integral. The integral as an adder. So, all of a sudden, just like calculus, and this is why calculus became such a big deal, as Newton and Leibniz and those people were working on it, is they have this idea of slope and rate of change and stuff like that, and they realized that if you could find the slope on a curve by this infinite process. But what made it such a big deal is the use of that in all those different areas. We just did a related rate problem where we talk about finding maxes and mins and optimization problems and stuff like that, right? Now, with area, just finding these odd-shaped areas, that's great if I owned a farm and I needed to know that how much and many acres I had. That was where this all kind of originated, because everything back in the day, a lot of that was based on property owners in the 1600s. You go back to that time period, right? That was who the rich people were the property owners. So a lot of that was a problem. But all of a sudden, as we realized, this whole idea of area of an odd-shaped thing can mean a lot more than just area, right? It can mean all these different things, net distance traveled, and all these different things. Well, here's another one. Here's another one to add to the list, where we can use this summing process, this integral process, to mean something that doesn't have anything to do with area. Doesn't have anything to do with area. So that's why that definition of the integral, using the sigma and the infinite summing, is such an important thing. Okay, here's what you guys could write down. So the result of all that we looked at is this. So let's take our little picture here. So we're looking at a little, so we got this curve, and we want to find the length of this piece of curve. The curve would be our f of x. We'll say here at the end, I'm not going to write x2 minus x1. We'll just call that delta x. That's change in x. And I'm not going to write y2 minus y1. That's just the change in y. So it's delta x squared plus delta y squared square root. That's just distance one. That's all that is. Okay? All right. Now, the red thing is the key. So what if I want to write this as an integral, if I want to write this as a summing process, okay, then what I have to do is I have to get a dx in there. Every integral has to have a dx at the end, right? To be an integral, it's got to fit that sigma as n goes to infinity, and we have to have that piece that disappears. We have to have that piece at the end, that width, that delta x, that goes to nothing, and then becomes the dx. It's got to be there. It's part of the definition. So I've got dx in here. I've got delta x in here. I just need it to go away. I need to get it out of the square root, basically, so I can have a delta x tacked onto the end. That's just something I need. So how could I do this? Well, we're going to multiply by a fancy 1, right? Everybody see how that's just a 1, right? Now, remember, whenever you multiply a square root times a square root, you can put them together. If you have square root 4 times square root 2, that's square root 8. If you have square root 4 over square root 2, then you can do it as a single square root like that, right? So you can do all that stuff. So what I'm going to do is I'm going to leave this delta x out here. And then also, if I have a fraction, like if I have 5 times 2/3, I could write that as 5/3 times 2, couldn't I? Right? Because it's really just 5 over 1, right? So that's what I'm going to do with this. So it's like I'm going to multiply this square root over with this, and I'm going to just leave that delta x hanging out over there, right? Makes sense? Kind of like I could do with a fraction here, okay? So I'm going to do that. So that would make this look like this now, okay? Because now what I'm going to have is I'm going to multiply. So I'm going to bring this over here. I got a square root over a square root. That could be in one square root. And if all of this is under square root of x squared, right? If square root of x squared is under this whole thing, I can split it apart into those two things. Make sense? Okay, so just some algebra trickery here. All right. Now, what's delta x squared over delta x squared? 1. And then this, remember, whenever you have a fraction, if I have 3 squared over 4 squared, that's the same as 3/4 all squared, right? Same thing. So 3 squared over 4 squared. So delta y squared over delta x squared is just delta y over delta x quantity squared. Okay, so just some algebra trickery. All I've done there is rearrange that. I haven't really changed. Every one of those lines is the same. They're equivalent. Okay, so they are all that length. They are all the length of this hypotenuse right here. They're the length of that guy right there. Okay, so now I want to add up how many of those. I want to do an infinite number of them. So as I do an infinite number of them, what happens to the delta x? The delta x. Smaller and smaller and smaller and becomes nothing. That's this part right here. So as I do a whole bunch of these, they get really, really close together. The delta x gets really tiny. Okay? Now what's another name for delta y over delta x? Slope. That's rise over run, right? That's slope. Now it's a slope between these 2 points, right? It's a slope between these 2 points. But as those little strips, as this hypotenuse, as this segment here gets littler and littler and littler, it becomes not the slope between 2 points, but the slope at just 1 point, right? It's getting closer and closer and closer to just the slope at 1 point, which of course is what? The derivative, right? So, two things are going to happen here. So, as we do more and more of these strips, as we do the limiting process, we do more and more of these strips, this is just going to disappear to become that dx thing, and this is just going to turn out to be the derivative, okay? Because those are going to get closer and closer and closer together. So, that's going to be f prime. So, lo and behold, that's going to turn into, oh, I didn't write it, okay. So, lo and behold, s is going to equal square root 1 plus f prime of x squared, and then that's going to turn into a dx, and that's going to be one of those little strips, and what do I need to add them up? I need the integral. So at the end of the day, my formula, what I've just done is created myself a little formula which is just nothing more than distance formula. But that is the formula for, now some books call it arc length. I don't really like to call it arc, because when I think of an arc, I think of part of a circle. It's not necessarily a circle, it's any curve. So sometimes it's called length of a curve, just length of a curve or curve length. But kind of the old, more traditional thing is called arc length. So either one of those, length of a curve or arc length. So, I mean, a very simple problem. Very simple. I mean, because typically what's going to happen, you're going to be given a function, and they're going to say, find the length of the curve from 2 to 5. Well, what are you going to do? You're going to do the derivative. You're going to square it. Plus 1, square root, write that out. Dx, 2, 5. Type in your calculator and get your answer. I mean, it is not hard at all. The more important thing about it is how we developed it and where it came from and how it fits in. But notice it has nothing to do with area. So this is a really good lesson here, in how we can use the integral to find something that doesn't have anything to do with area. Now, we've already talked about that as far as with units. We've talked about how we get net distance and velocity, and we get that kind of stuff because of the units. But it all did kind of relate to area. This is really the first one we have that really has no connection at all to area. It's simply using the integral as an adding machine to add up a bunch of little pieces of something. In this case, it's adding up little pieces of distance, little pieces of length. Okay. Now, I think it was in a sense doing that before. If this was a velocity function here, then we had meters per second times little pieces of seconds, right? Well, meters per second times second is in meters. So we did have that integral adding up little pieces of distance there too. That's why it was net distance. But we can always show it as a graph. We could show the velocity graph. We could do the area under it, and that was distance. Okay? This is one where the area really would have no connection. The area of this thing would have no connection to that. Now, the last thing I would say, though, related to what I just said. So if I give you, and I think you're going to have a homework question similar to this. If I gave you this, everybody get your calculators out. Okay, if I just give you this integral, right? If I just gave you this integral right here, type it into your calculator, see what you get. What do we get? Now, we've said all along that a definite integral is just a number. A definite integral is just a number, right? It represents a number. Now, in the beginning, we said a fixed piece of area, right? But it's a number. A definite integral is a constant. It's just a number. There it is, 8.268. Now, that number can have a variety of meanings, right? Like 10. 10 could be, the number of people in class today. Oh, well, I guess I'm here. So, is that 10? There you go. 10 could be the number of people in this room. 10 can also be the amount of money in my pocket, right? 10, I mean, it could be a variety of things. It, you know, so this number could represent, this integral could represent a variety of things. Well, it could for sure represent two things, for sure. Now, the obvious one is the first one we learned. This could represent area, right? This integral could represent what area? Under this curve, now let's go to our calculator and let's do, I should have had hats on today, whatever. Go to your calculator, and I'll pull up mine even too. Go to your calculator and let's graph this curve. Okay, so I wonder if I go to, I'm kind of intrigued by this relation stream for graphing. I wonder what other differences are under there. I'm gonna go to that stream. 1 plus, I have, like I was saying yesterday, I have not done much with this because it was new in the operating system. Okay, there it is right there. Now it's not a parabola. It kind of has that look to it. But it's, let me move this out of the way. Now there is a way on here. There is a way under analyze. Let me see, integral. What did we say we wanted to do? Can I type in a 1? I feel like I should be able to. And then let's type in a, what just happened? There we go. Oh, that's kind of cool. I don't use this very often, right? But there's the integral. It's so much faster on the home screen, right? On the calculator, you can just do the integral and get your answer, right? But, right, 8.268. So that piece of area is 8.268. All right. Now, so it looked like that. It kind of came down here. It kind of went like that. And boom, boom. Okay, that was 8.268. What else could this represent? This could also represent length of curve. What curve? So, this is square root 1 plus 2x quantity squared, right? I like what you were doing there. That means f prime is 2x, which means f would be x squared plus, does a c matter? If you take x squared and just shift it up and down, is the length from 1 to 3 going to change? It is not going to change, right? So we don't worry about the plus c. So this would be the parabola x squared from 1 to 3. This piece of curve right here should be 8.268. This area is 8.268. This piece of curve is 8.268, right? Okay, now I think the calculator does that too. Let me, I'm not sure if it does it under here. Let me get rid of this. Let's graph x squared. That's why I'm curious what the different, oh, I still got that area on there. How do I get rid of that? Hit what?
You usually put your cursor over it.
Oh, that's like an undo? Is that undo? Has that always been there?
Yeah.
Thanks for telling me. I don't think that's always been. Do the calculators have that back here?
Yeah.
Is that your calculator? Do all of them have it?
So
Mine too.
So this controls V, right?
Oh, Control Z. So I think I know that. I think I've done Control Z. Okay. Anyway, but if I just go over, do what now? If you It's like if you hit enter and then they blink, then it's like selecting them. You can delete. Okay, so now I did my undo. Can Control Y, will that redo? Isn't that usually a redo? Control Y? Doesn't look like it. Okay, anyway, well, let me go back. Okay, so delete x squared. All right. So now I think under Analyze Graph, no, I thought there was somewhere. Let's see if I trace. Okay, let's see. Let's go to the calculator screen. Let's go to the CAD. No. Let's go to the book. Aha. So the book over here is like the library, the catalog of all the different functions. If you go to that, and then this has them all in there, I think. I think this has everything. At the bottom of this number 2 here. Yeah. Number 2, if you go under calculus, arc length, here it is right here. Arc length, expression, variable, start, end. So it's just a function for you programmers in here. It's just a function that's a series of statements that are I think there you go. So just on your calculator, you can pull that up. And so if we type in x squared, comma, now I would not, because on anything we do, you're going to have to set up the integral, right? I mean, that's what you're going to get the points for. So it says do the arc length, right? You're going to set up the integral and all that. But it's just kind of fun to check, okay? So it was function, then the variable, so with respect to, and then 1, and then comma 3, and enter, and I'm missing something.
I don't think
that's not a comma, is it? It's a decimal. Oh, that's fun. And there it is, 8.26. Okay, so just kind of some fun extra stuff there, but it's not, the important part of it is just this form. You're gonna have to memorize that, right? It doesn't show up a lot. I don't think we've seen it in the packets. It is something that could be on there though, so I'm not sure. It just doesn't show up that often. So, but it will be in our Chapter 7 quiz that we do. Okay, so. And how we get it, but just understand that a definite integral, as we learn more and more and more, a definite integral could mean a lot. It could come from a lot of sources, right? At the end of the day, a definite integral is just a number, right? But what that represents could be different depending on the problem, right? So it could be a piece of area under that function, or it could be the length of the x squared function. But you kind of have to deconstruct it. And it has to fit this 1 plus f prime squared kind of thing for that to work. All right, so your homework is the next 2 lines. There is a new LH packet. Now, this LH packet is thicker than other ones I've given you, and that's because it's the whole chapter out of the book. So, in the other LH packets, I've just given you kind of the assignment pages where the problems are. But this one I gave you the whole section because it's got some examples of stuff we may want to be looking at various times. So So the book problems, so the next line there, so 6, 9, 12, 39, and 43, those are, I think, pretty much all arc length problems, I believe. Well, they might not be. I think some of them are some unit kind of problems and stuff like that, possibly, but I think the rest of them, 9, 12, yeah, 39 is an arc length, 43. So except for 9, they're arc length. The LH packet is what we learned the other day. Top minus bottom, right minus left. So those are area between curves kind of problems. So some of them they draw the picture for you. Some of them you have to draw the picture. And I think you can decide whether to use either horizontal strips or vertical strips. Okay? So you do what you think would be best. And again, we're back in this thing for the solutions, and be careful because it's really falling apart. But the solution to the LH package is here if you want to double check those. Okay? All right. That's all I got. So the rest of the time is work. Yeah. Yes. Okay, so
Nothing, no homework is usually done. And that would be,
Oh, yeah, you're gonna be gone. Are you gonna come back for like 3rd and 4th block? Or will it still be going on then?
it'll still be because the running rest will start at 11:30. So
Yeah, but this is like, we'll all start at 8.
yeah, but they do all the field events. They get those done basically. Then they do the running race. So it seems to me it's usually done by 3:30.
We already Columbus today, so.
No, we go to North Platte. But my guess is, yeah, the Columbus is just the boys.
Is it like
But-
our flat?
Yeah. Yeah. Yeah, it's Saturday. We always go there on Saturday, the boys.
Is it boys and girls?
North Platte is, yeah. So, hey, everybody else has boys too, but us. Because the boys are always, boy, yeah, it's good. All right. Yeah, let me think up here, guys. I think, no, that's not an option.
we had homework for last weekend.
I know, that's because all the bugs. Why we can't do it again.
That's what's saying. You have to ask, you wouldn't have asked if you wanted that. Oh. New packet.
Give it to you today.
Something after work out. Well, somebody did a good one. Are you getting the one we had last time?
It's Kinsley?
Is that who it was?
I think that's
All she did was like, wow, that this shit, she's been.
Jeez, I'm sure you got her going. You enjoy that. All right, so at the top of this, hey, let's do this. At the top of this, let's write, I gotta think about what this one is. Let's see, this one is, I gotta think what to call this one. Hang on.
Extra credit.
Extra, good one. As you always have good
And we
ideas.
probably lose 10 points actually.
Always have good ideas.
It's 300 bonus points on the multiple choice. 900 bonus points. Oh, not bad. Ooh, I thought the semester's. That's way more. I know we get that. What?
Okay, this is not that.
You never had that. Yeah, we get like 100.
And Sam Dreesen's class.
Okay, so this,
We had like 3,000 points. Everything we did was 100 points. Tests. So like we'd have like 30 grades and everything we
Mr. Missions.
just like that.
Yeah. Like the essays are 300. And then
okay, this is, so right at the top up here, right up here, this is the 2016 multiple choice test.
92 questions.
Now, well, no, it's not 92. The first section, the first 28 are numbered 1 through 28. That's the no calculator section. So remember, the first section is no calculator. And then the next section starts with 76 and goes to 92. It's 17 sections, 17 questions. Now, this year's AP test, instead of 28 and 17, it's going to be 30 and 15. It's going to be 30 no calculator and 15 calculator.
So 400.
So, but this is actual, this was the actual test. So you see this one's got the actual questions. That's why it's got those A's all across the top. And then the next section has B's all across the top because it's part A and part B. Part A is the no calculator, part B is the calculator. That's why it also says unauthorized copying or reuse of any part of this page is illegal.
Unauthorized?
I think this is authorized.
I'm calling it. I don't want to do this.
I refuse to do this because it might be illegal.
I don't like I
No, I think it's legal. So anyway, tomorrow we will be
did. Last page.
working on trying to complete that packet.
You know, like 6.
Uh-huh.
So when we do the derivative, is that why that equation like that?
Right. So let me go back to. So what does it say? It wants you to do the.
Yeah, it says write an integral. It gives the length of the curve as y equals x squared plus 1 and from x equals 0 to x equals 1.
Right. This is the one. This is the integral that gives you the calculus.
So I do y prime.
So you need to do the derivative of the curve that you're doing there, and then square it. Just put it into that
Let's
form.
see if I can fit it.
Just put it into that form. That's all you do. And then find the answer. If it says write the integral, I mean they want you to.
This was
find the length.
way bigger when we had this.
So I would have like, if I had 2x plus 1 or x squared plus 1, it would be 2x and I would square the 2x.
Quantity squared, right? So it'd be right.
Then
Which you can go ahead and square, or you can just leave it 2x quantity
it would
squared.
just be from 0 to 1.
Right. That's it. Yeah.
So bad we didn't Google the trebuchet in this class.
No.
Why?
Because that's stupid.
No, it's not. So then the homework for Monday
Is as much as you can in that whole packet.
and then
Right.
also the homework for tomorrow is.
Because on the actual AP test, those 45 questions, you would get 105 minutes to complete those. So tomorrow in class, we have 85 minutes. So, right?
So you gotta read it.
You should get 80% of it done. Right? Just saying. Well, I'm not sure that's how you guys work. Right. I'm not sure how you guys work when I'm not here. See, I was going to say, that's true. If Will is not here, first block may. Well, I do know when I walked in that day and the sun was here, everybody was in their desk with pencils kind of in hand, and Will was sitting over there on top of a desk doing absolutely nothing.
I was just watching your video.
No, we got done with
No, the video was
I
long.
was talking to the sub.
The video was long over.
She was worried. She had a call from the doctor.
It's because we had it 1.5 speed.
Do we have to do 20
Yeah.
sub intervals of the
We put your video on like
Oh, is there? No.
1.5
No.
speed.
'cause it was.
Well, here's what that would be. Yes, you can, because that would be
I
the,
understand it.
where's that at? Number,
6A.
okay,
You can watch these videos.
Yeah, I watch like the Susan, yeah, I can't.
all right, listen up here, listen up. These students from second block are bothering us. Because usually this class is serious. Number six, okay, number six, couple of things. Which, you know, you guys have had like 40 minutes to work, 15 minutes are gone, nobody's on number six yet, this is the first one. But anyway, it must be those people from second block. So number six, write an integral that gives the length of the curve, da-da-da. Okay, so you write that integral. Now, one of the things, okay, so what does number six say? Number six says, use a midpoint sum with 20 equal subintervals to estimate the integral. Part B says, evaluate I exactly, hint, use the table of integrals. Okay, so let's talk about that. First of all, how would we do a midpoint sum with 20 subintervals? Oh, say it again. That area program I gave you on the calculator. Remember, if you're 10 or more, you get to use that program. So, what's that? It was called area. Area. So it was in your. So go onto your calculator, go to the area program, put in. So you got your integral written, right? You get your integral written. So you go on that area program and do an M20. Then it says evaluate I exactly. Use the table of integrals. What they're saying is there is no antiderivative for it, right? There is no antiderivative for what you're going to come up with on that one. Matter of fact, most of the time when you do an arc length one, it's not going to have an antiderivative you'd be able to do. Well, in the old days, one of the ways we would do it is go to a table of integrals, and we used to talk about that a little bit, but at this point, with technology, what's the point? But you would look up in a table of integrals how to do it, and then you would type it in from there. Well, our calculator is our electronic table of integrals. So when it says find it exactly for part B, just type in your calculator and get the answer from your calculator. Okay? So usually evaluate I exactly would mean do the antiderivative. But it doesn't work in this case. That's why they said table of integrals. Okay? So do your area program for part A and then just type in your calculator.
Type that.
Type the integral, yeah, just like you normally would.
Wow, I got 1.33.
That's what I got.
So this is our last chapter of the year.
I doubt it.
How many more do you go? How many more chapters?
8 more weeks.
I can wish.
This is our last chapter.
Is it? Then what do we do
Take us to
with
the
this?
rest of the year.
Well, we're going to be, like I was saying the other day, I guess I could.